let's see, maybe the fastest way is to go to table of contents. I had a doctor's appointment which screwed everything up today, and so I'm just okay, so let me just review the very basic things. The basic thing is that the integral of an analytic function around a closed contour inside a domain of analyticity. So here's a domain of analyticity, and the contour C is here, and it's a closed contour. That's what the O means here. And that's 0. And from that, we derive Cauchy's theorem, which is that so that's Cauchy's theorem. This is Cauchy's formula, and essentially everything in analytic function theory follows from these two formulas. And of course, the second formula followed from this formula, and this formula follows from the definition of analyticity, namely that the derivative of the function exists no matter how you take the limit, no matter how, in other words, f prime of z is a limit, f of z prime minus f of z over z prime minus z, and this limit must exist at z no matter how z prime approaches z. And this then implies that implies this. There's a technique that's often used in complex variable theory, and it's something that I call a ghost contour. And an example of it can be, is how we might solve this integral dx over x minus I, x minus 2I, x minus 3I. So what we have there, if we replace x by z, is we see we're dealing with an analytic function that has three poles in the complex plane, one at I, one at 2I, and one at 3I. And the question is, well, how should we do this integral? Well, one way of doing the integral is saying that we add what we can call a ghost contour around the lower half plane. And this is a ghost contour because 1 over the absolute value of z minus I, well, I guess it's the product of all of them, z minus 2I, z minus 3I, this goes to 0, and in fact, if we imagine that z has is roughly of the order of r, where r is this radius, then what we have here is that this magnitude is, when you take into account the length of this curve, that length of the curve is pi r, and so what you have is pi r over r cubed, essentially. And that goes to 0 as r goes to infinity. So in other words, you can add a ghost contour that goes from where the ghost contour has z equal to r e to the I theta, and theta goes from 0 to I guess minus pi. from 0 to minus pi, and anyway, that extra Gauss contour is 0. So now what we've got is we've rewritten this as an integral of an analytic function in which the contour is entirely within a region in which the function has no singularities. And so this is just 0. So that's an example of how you can avoid a lot of work by adding a Gaussian contour. Another example is the Fourier transform of a Gaussian. And this is something that I promised that we could do a long time ago. And the idea basically is that we're integrating the integral that we've got is an integral from minus infinity to plus infinity. Oh, wait a minute, is this the... Well, before we actually do the Gaussian, let's just consider e to the minus x squared dx. That's what we're actually talking about. It's actually m squared x squared. So we want to do this integral, and we can say, well, this is a complex integral, e to the minus m squared z squared dz, and we're integrating this way on the real line. But now we can imagine we're going out to r, and we're coming back. Let's see, did I call it r? Yeah, r. Going from minus r to r, and we're taking the limit r going to infinity. But then we're going to add a Gauss contour, and the Gauss contour is going to go up to r plus ic, and then it's going to go to minus r plus ic, so it's going to go this way, and then it's going to go down like that. Now, this function, e to the minus m squared z squared, is certainly analytic. And so what we've got then, what we can say then, is that 0 is the integral from, let us say, minus r to minus r, minus r to plus r, dz e to the minus m squared z squared, plus an integral from r to r plus ic e to the minus m squared z squared dz, plus an integral from r plus ic to minus r plus ic e to the minus m squared z squared dz, and then plus this final amount, which is an integral from minus r plus ic to minus r e to the minus m squared z squared dz. So those are the four edges of this rectangle, and this integral has to be 0 because this is an entire function, let alone an analytic function. On the other hand, as we take the limit of r going to infinity, this integral is 0, and this integral is 0, because the absolute value of e to the minus m squared z squared is the absolute value of e to the minus m squared, and z squared is r plus ic squared, and this ic, the cross term introduces a phase, the square of c just introduces a small change, but the real business is e to the minus m squared r squared, and that goes to 0 very rapidly as r goes to infinity. On the other hand, this thing is an integral let's see, wait a minute, let me make sure I've got everything straight. There to there, that to that, that to that, that to that. Right, okay, that's all. Right, so, I'm sorry, I crossed out the wrong one. This one is not 0. And in fact, so what we have here is that 0 is, if we just make, is an integral from minus r to r, or minus infinity to plus infinity, of dx e to the minus m squared x squared. And then this term is plus an integral from, well, it's e to the minus m squared, and now this is x plus ic squared dx. But we're going from infinity plus ic, well, we can just say infinity, since I've put the ic in explicitly. We're going from infinity to minus infinity. On the other hand, if we switch the limits, that gives us a minus sign. And so we get the rule that integral from minus infinity to plus infinity, e to the minus m squared x squared dx is equal to the integral from minus infinity to plus infinity, e to the minus m squared x plus ic squared dx. So that's the result I wanted to get to. And the way we got to it was we introduced a ghost contour. That is to say, a contour on which the integral of the analytic function just is 0 in the limit of r going to infinity. This is the formula, though, that we need to show that the Fourier transform of a Gaussian is a Gaussian. Because what we do is, I thought there was a question. Okay. What we do is let c equal k over 2m squared and divide both sides by pi, and then what we've got is a formula for f tilde of k, namely, well, I'm sorry, I skipped something. This is a famous integral. This is an integral of a quadratic form, and so this thing, minus infinity to plus infinity, dx e to the minus m squared x squared, this is equal to square root of pi over m. And so f tilde of k, which is an integral dx over square root of 2 pi e to the minus m squared x plus ic squared. Well, this is, I'm trying to do it straight on the board, and then also, so the actual definition of the Fourier transform, of course, is minus I kx e to the minus m squared x squared, and this then is 1 over square root of 2m e to the minus k squared over 4m squared. The idea here is that this is completing the square trick, which I may have skipped. If we let c be k over 2m squared, then this formula is dx e to the minus m squared x plus ik over 2m squared squared, and that's equal to that. And so this term is integral dx e to the minus ik x, that's the cross term, and then e to the minus m squared x squared, that's this term, and then this thing squared is going to be e to the k squared over 4 m squared. And so consequently, from this formula we get this result, namely that you just multiply by e to the minus k squared over 4m squared on both sides, and you get that. And together with the fact that this integral is square root of pi over 1. Anyway, filling in those arithmetic steps, we get the Fourier transform of Gaussian is again a Gaussian. And as I mentioned to you when we were discussing Fourier transforms, if m squared is big, then this is peaked about x equal to 0, but then the Fourier transform spreads out over all k. And if on the other hand, m squared is very small and x is spread out, in that case, the Fourier transform is peaked at k equals to 0. There are many other examples of, let's see, maybe I'll do some of these with the computer to save time. And by the way, I only have one candy left, so the first person to ask a question gets the remaining candy. All right, here's another example of the use of ghost contours to do, in this case, a Fourier transform again. So this is a Fourier transform of 1 over k squared plus m squared. And how you do the Fourier transform, how you do the ghost contour depends upon the sign of x. If x is positive, then this exponential function decreases when the imaginary part of k, when k is in the upper half plane. And so in that case, you add a Gauss contour that goes around the upper half plane, sort of around the North Pole. And so you let k equal to r e to the I theta, for theta going from 0 to pi, and dk then is this. And on the other, so what we've got here as far as the magnitude of the Gauss contour is we've got a factor of r from the perimeter of the contour, but we're divided by k squared here, and then the thing also exponentially decreases. So we can certainly add that contour. And then when we factor the denominator, we see there are two poles on the imaginary axis, one at Im and one at minus Im. And so what we've got then is we can, once we have the Gauss contour, we can then deform the contour and shrink it so that it's just around the pole at k equal to Im. And when we do that, the other part here, where k is Im, this thing turns into 2Im, because k is essentially Im. So that's the 2Im term. And then you're just doing this, let's see, I think there's another thing that since k is Im, this is e to the minus mx. So that's where the e to the minus mx comes from. And then you just have the integral of k minus Im integrating around, and that just gives us a 2 pi I. And so we get this as the answer. For x negative, we have to we again add a ghost contour, but now we go over the south pole, and we let theta be, say, between pi and 2 pi. Then it's basically the same thing. It's just that we do the pole, we integrate around the pole at minus im, and so we get minus 2im here, we get e to the mx there, but remember x is negative, and so we get this expression. Combining the two, we get the answer is pi over m e to the minus m times the absolute value of x. There's a derivation, you can apply that and derive Bessel's formula for the Coulomb-Green's function, but I think we can skip that. I can do it tomorrow in the problem session if you want. By the way, does anybody have any question about anything? For example, we're going to have a midterm exam on Thursday. Does anybody have a question about those chapters? Yes. So you get the candy. Good catch.
I wanted to know, like, how many questions will be coming, and are we allowed to bring a formula sheet, or?
You can bring the book.
What?
And yeah, you could bring a formula sheet, yeah. And I don't know how many questions there will be. I haven't made the test up yet. I also haven't done anything about moving to the new building, so I'm a last-minute person.
Okay.
Naturally, obviously, then I was delighted to hear that the move was postponed for a week. Okay, so here's another example of a ghost contour. This is more complicated, but maybe it's worth doing. So what you do here is you let k dot x equal to kr cosine theta. R is the absolute value of x. And you do this usual manipulation to get to here. And these are manipulations that you are familiar with from your courses in mechanics and electrodynamics and quantum mechanics. So then what you've got is you've got essentially the same thing as in the previous case, and consequently you get this expression. And this is the formula that Yukawa proposed back in 1930 or so for the potential between two hadrons. What had happened was the muon was discovered at that time, and he thought that the muon was the particle mediating force between two hadrons, but in fact it was the pion, and but his formula was right. It's just that the particle identified wasn't the one that had been, the right particle wasn't the one that had been just discovered. So here are some more examples which I think we'll skip. I can do in the problem session if you want. Anyway, these ghost contours are very useful. The thing you've got to check simply in each case is, does the function go to 0 on the contour fast enough so that, faster than the length of the contour? That's essentially the question, or the issue. Okay, now we're dealing with logarithms and cuts. And the basic idea is that if you have an ordinary function, always a function maps a number in its domain to another number. And so f of z goes to a unique, z goes to a unique f of z. let me see, maybe I'll do some of this on the board. So I guess I'll turn on the lights in the back. I didn't have time to erase the board. So always z goes to f of z, and f of z is unique. Now for some functions, given f of z, you can figure out what z is, and you can go backwards. Then we say it is 1-to-1. So a function is 1-to-1 if the map between the domain z and the range, the values of f of z, that's a 1-to-1 map, and you can go both ways. So for example, on the real axis, e to the x goes to e to the x. For every real x, you get an e to the x. But notice that e to the x is always greater than or equal to 0. In fact, if x is finite, e to the x is greater than 0. So this is actually 1-to-1, but when you're going backwards, you're taking the positive part of the real line, and when you go backwards, you map that onto the whole real line. Whereas, and that's the function that's, in fact, it's log. It's the log function. So log e to the x, of course, is x. So that's the inverse function. Whereas e to the x takes you this way. From any real number, it gives you a unique positive number. And the inverse, the log, gives you a unique log for every positive number. But, of course, in the complex plane, it's no longer the case. And the root of all of this is I guess, that you see e to the z plus 2 pi I n is equal to e to the z for n in integers. So this is why you can't go, this is why the exponential function isn't 1-to-1 on the complex plane. And so the log of e to the z, well, it is z plus 2 pi I n. And this is true for any integer n. And so there's an ambiguity here. And so what people do is they set up conventions and they decide, what you're going to have to do is you're going to have to set up a convention. In each time you do a problem, you're going to have to decide what your convention is, what n you're going to use. And so basically, what's your convention for the logarithm? This, just to give an example here, suppose we're dealing with z to the a. Well, by definition, this is e to the log z raised to the a power, right? Because e to the log z is z. but this is then e to the a log z, and so that's e to the a log r plus I theta plus I 2 pi n, because if z is equal to r e to the I theta, it's also equal to r e to the I theta plus 2 pi I n. And so the log of z is the log of r plus I theta plus 2 pi I n. And if a is an integer, then this doesn't matter, because what you've got then is e to the a, is you've got e to the z, and the ambiguity part is I 2 pi I times a n. If a is an integer, then this thing is again an integer, and this e to that is just 1. And so, for example, if we have square root of z, well, that's going to be e to the 1/2 times log r plus I theta plus 2 pi I n. And so that's square root of r being positive, e to the I theta over 2, but then we have e to the I n pi. And e to the I n pi is minus 1 to the n square root of r e to the I theta over 2. So there's a choice of plus or minus that comes from your convention, what n you're dealing with. And one of the problems, exercise 6.30, is to show explicitly what the square roots of a complex number are. And they're rather more complicated than one would think. So maybe I'll show them on the screen rather than writing down. So there, here, for example, for the square root, what we do is we have to define the angle theta, and we can say, well, theta goes from, here, let me actually use the board now. The two popular conventions are that theta starts from 0 here, increases until it gets to 2 pi, and then then it drops by 2 pi as you cross the cut on the positive real axis. So this is called the cut. The other popular convention is that both conventions agree in the upper half plane. But the other one is that see here, theta is between 2 pi and 0. Here, it's between pi and minus pi. So here, we go to minus pi. Here, we go to plus pi. Here, we go 0 all the way to 2 pi. So those are the two popular conventions. You can put the cut anywhere you want. And if you put the cut on the negative real axis, then an explicit formula for the square root of z is this. On the other hand, if you put it on the positive real axis, an explicit formula is that. And if you're writing a Fortran program or program in some other computer language, and you're dealing with complex numbers, you may need to use formulas like these. You may find them absurdly complicated. I agree, they're more complicated than one would expect. I think that the reason they're so complicated is basically that the natural description of things in the complex plane is in terms of radius and angle, and here we're forcing the description to be Cartesian in terms of x and y. And so the complexity of these formulas is a reflection of the unnaturalness of the Cartesian description of the complex plane. On the other hand, there are senses in which it's simpler. It's obviously easier to add complex numbers if you use x plus I, y. On the other hand, if you want to multiply numbers, it's easier to use a polar expression, r e to the I theta. So, if this is the function, for example, you could put the definition, you could put the cut either on the positive or negative real axis. And then what happens because of this particular formula is that the function f of z winds up having a discontinuity only between -1 and +1, because the two minus signs that occur when you have x greater than +1 or less than -1, and no matter where you put the cut, whether you put it on the positive or negative real axis, you get two minus signs which cancel when you're outside of the interval from -1 to 1. So here are more examples of such things, and I guess maybe we should go through one of them. Let's in fact do this one. Here we've got x, a real number somewhere between -1 and 1, and well, this is a rather complicated example. We put the cut on the positive real axis, and then what we see is, because the x is squared here, and in the numerator we would have 1 power of r, we would have r to the 1 plus a. 1 plus a is less than 2, and so we can add a Gauss contour at infinity. And so what one does is, finally, is to do this. We add, actually there are quite a few extra contours here. We add a Gauss contour G plus, we add a G minus Gauss contour. We add two contours here that are going to cancel each other, and then we wind up with a clockwise loop around the pole. And then, because we added this contour here, if we want to get something that's 0, we have to add an integral from infinity to 0 going just below the real axis. So the integral of the analytic function around this contour, say going from here up to here, down here, along here, up around there, down here, around the pole, back this way, and then down to here, that is a closed contour, and it's a closed contour inside a region where there are no singularities. In other words, this point here is outside the contour. As you can see by the fact that you could move this, you could shrink this over this way, you could shrink this that way, you could shrink this in. So you could suck the whole thing in to a point somewhere halfway between the singularity and the origin. And those changes of the contour would make no change in the value of the closed contour integral. So then you make some observations based on the function itself, and it turns out these two contours cancel. These two add. The G plus and G minus are both 0, and this is a simple exercise in Cauchy's formula. So in other words, to do the integral around the pole, we have a double pole there actually, and remember that if you differentiate Cauchy's formula, you get his formula for all the derivatives of an analytic function. And in this particular case, it's this. And then if you look at the function, the integral below the cut, well, below the cut, it's x minus I epsilon plus 1, which really cuts no ice. But up here, we have e to the a log x plus 2 pi I, and it's probably a robocall. Oh no, it's my wife. Yeah, I went to Costco. I don't know, maybe it was a popsicle. Anyway, I went to Costco.
Oh, did you go already?
Yes, but I forgot the tomatoes.
Oh, that's what I was going to say, if you were at Costco to get tomatoes.
Yeah, I forgot tomatoes. Okay.
Okay.
All right, bye. Sorry. So this gives us e to the a 2 pi I, and which comes out. And the thing that's left is just, apart from a minus sign, the original integral that we started with. So the total contour integral gives us the integral around the double pole plus the integral we were looking for, and then the integral I minus that we just did. And so resolving that, we find that I is pi a over sine of pi a. So that's a somewhat complicated example of such things. Okay, so now, now we have something that is maybe best done on the board. It's conformal mapping, and it's a simple idea. So the idea is we go from z to f of z, and the point is that angles are preserved. Now, why is that? Well, they're preserved because f is an analytic function, and they're preserved as long as f of z isn't 0. They're preserved at f of z, at z. In other words, the angle at z. Let's consider what the angles are. First of all, dz is we can think of as some epsilon e to the I theta, and consider another dz prime. Well, this will be epsilon e to the I theta prime. So these are two. So this is theta, this is theta prime, and this is dz, this is dz prime. So the angle between them between dz and dz prime, the angle phi, say, is equal to theta prime minus theta. Now, that gets mapped into f of z plus dz, which is f of z plus f prime of z dz, and, or I wanted to say df. So let's look at df. df is f prime dz, and df prime is again f prime of z dz prime. So these two small displacements in the z-plane get mapped into two other displacements, df and df prime. And now, if we compute the angle between them, this phi, of course, the way you compute that angle is you take dz prime over dz. The epsilon cancels, and you get e to the I theta minus theta prime. Here, you're going to have df prime over df, and so this is f prime of z divided by f prime of z, dz prime over dz. The f primes cancel, and notice that the f primes canceling is at the very heart of analytic function theory. That definition of analyticity is that the derivative exists no matter how you come at the point. And so here you can come at it via dz prime, here you can come at it via dz, and the same, you have the same f prime of z. And so this is e to the I theta minus theta prime. And so that's saying that the angle, this is e to the I phi. So phi is defined as theta minus theta prime. It's defined in the z-plane. And so then we see that it gets mapped into, when you take the ratio of df prime over df, you get the same angle because you just get dz prime over dz. Now, there's one caveat here, and it's that if f prime happens to be 0, I said previously f equal to 0 was a problem. It's when f prime of z is 0. Because you see, if f prime of z is 0, then these formulas aren't right. So suppose f prime of z is equal to 0, then df prime is going to be 1/2 f double prime of z dz squared, dz prime squared. And df is going to be 1/2 f double prime of z dz squared. And so then df prime over df is going to be dz prime squared over dz squared. And that's going to be e to the 2I theta prime over e to the 2I theta, or e to the 2I theta prime minus theta, or e to the 2I phi. So if the first derivative vanishes, then at a certain point, then the mapping isn't conformal at that point, and instead angles are doubled. If the first non-vanishing derivative is the n, then the angles are multiplied by n. So that's basically conformal mapping, and there are various examples of that. So that's what I've just gone through. If we're dealing with z to the n, well, z to the n at the origin has only one non-zero derivative, namely the nth derivative at the origin is n factorial, but all the other derivatives at the origin vanish. And so that means that the angle changes by a factor of n. On the other hand, if you're not at the origin, then f prime is always non-zero. And a famous example is the Mobius transformation. This function, az plus b over cz plus b, maps straight lines into lines and circles, and maps circles into circles and lines. And the only exception is when AD equals BC. In that case, the numerator is proportional to the denominator, and f of z is just b over d. Let me see if I can. So Cauchy's principal value, that's something that's used a lot in physics. I don't think it's used very much in mathematics classes, but it's used a lot in physics, so it's important to understand. So we're imagining that f of x is differentiable or analytic near the point at and near the point x equals 0, and we want to evaluate a certain integral on the real axis. And we're imagining that we have f of x divided by x minus I epsilon. And as usual in physics departments, epsilon is a small number, small positive number. And A and B are both positive here. So the first thing we do is what Cauchy did, namely he regularized the pole at 0. And so what he said was he redefined k as being an integral from minus a to minus delta of the same function, plus an integral from minus delta to delta, plus an integral of delta to b. And now in the first and third integrals, the epsilon doesn't matter, because epsilon, we're taking the epsilon to 0 first and then delta to 0. So what we have then is an integral from minus a to minus delta of f of x over x, plus an integral from delta to b of f of x over x. And then we have this term here where we first take epsilon to 0 and then delta to 0. So Cauchy defined this limiting process to be his principal part. So the principal part of an integral is, or the principal value of the integral is a limit, delta going to 0, and you integrate from minus a to minus delta, and then you integrate from delta to b. And if the function f is nearly constant, then this thing is finite, and it could even be 0. The Cauchy definition, the principal part, or the principal value, is at a point y, is again you integrate from minus a to y minus delta, and then you go from y plus delta to b. And so using Cauchy's principal value, we can write this quantity k as the principal value of the integral plus a double limiting process here. Now for the second, to evaluate the second integral, we use the analyticity of this function f of z, from which on the real axis is just f of x. And so we write f of x to be f of 0 plus x times f prime of 0. And so we have these two expressions. In other words, we approximate f of x by f of 0 plus x f prime of 0. And that gives us two things. The f of 0 comes out, and we have this double limit of dx over x minus I epsilon. And then we have this thing, f prime of 0 times this. Well, this thing here, because x is in the numerator and the denominator, this is a finite expression. The magnitude of the thing is the magnitude of x divided by the magnitude of x. Maybe I should write this down. All right. X, the magnitude of x over x minus I epsilon is the magnitude of x divided by, well, the square root of x squared plus epsilon squared. And so this is something that is that's something that's of order 1, and in the limit of epsilon going to 0, it's exactly 1. And so we have the integral of 1 from minus delta to delta, and that's just 2 delta. But we're also taking the limit of delta going to 0. So this whole thing is 0. So what we're left with as the second part of k, the complicated part of k, in other words, we've defined away one part of k, and then we have the second part of k. The second part of k is then just f of 0 times the double limit. Well, this 1 over z minus I epsilon obviously is analytic in the lower half plane, so we can deform the straight contour from x minus delta to x plus delta, from x equal to minus delta to x equal to plus delta into a tiny semicircle that avoids the point x equals 0. So we set z equal to delta e to the I theta, let theta run from pi to 2 pi, and that gives us this expression here. And now we set epsilon equal to 0 and do this integration, and so dz is I delta e to the I theta d theta 1 over z, see we're at z now because we're on the contour, it's delta e to the I theta. The delta e to the I theta cancels, and so we just have an integral d theta from pi to 2 pi. That's just pi, and the I comes out. So altogether, k is the principal part of the integral, the principal value of the integral, and plus I pi times f of 0. And another way of thinking about it is that it's the limit epsilon going to 0 of this integral is the principal value of the integral plus I pi, the value at f of 0. And so physicists rewrite this as 1 over x minus I epsilon is the principal part of 1 over x plus I pi delta of x. Because if you substitute in this expression the right-hand side, it gives you the, if you substitute in this expression the right-hand side of this expression, you get the right-hand side of 6.244. And of course, if you flip epsilon to minus epsilon, you get this expression here. I say of course, but well, all right, you just take the complex conjugate of the first equation and you get the second equation. That's one way of thinking about it. And notice that x could be any real number, so it can be x minus y. So what one uses in physics departments all the time is 1 over x minus y plus or minus I epsilon is the principal value of 1 over x minus y minus or plus I pi delta of x minus y. So there we see two methods, two great figures in mathematics coming together in one formula, Cauchy giving the principal value and Dirac giving the Dirac delta function. And then it's something that we use all the time in physics. So here's an example. Suppose we wanted to evaluate this function. Well, it'd be the principal value minus I pi delta of x on this. But now this thing here is completely odd. And so the principal value of that is just 0. On the other hand, the other thing, we just put x equal to 0, and we just get 1. And so the integral is just minus I pi. So we use this trick to evaluate this integral, and we just get that. All right, here's an example of an integral that we quoted before. We used it in chapter 4, and so it's worth maybe doing. So this integral I sub s, I don't know why I called it s, I guess s for sine. The first thing we do is we write sine as an exponential. Two exponentials, e to the ik minus e to the minus ik over 2i. Then we can, and that's integrated from 0 to infinity, but then we can rewrite that as an integral from minus infinity to plus infinity. And we actually mean the Cauchy principal value of this integral. And now, changing that, realizing that the Cauchy principal value is the integral k plus I epsilon plus I pi delta of k, we then can do these two integrals separately. This one, obviously, we just get pi over 2 essentially. That's just eyeballing it, I get pi over 2. Yeah, that is pi over 2. And this one actually is 0. And what we do is we add a ghost contour in the upper half plane, and the way we get away with that is, well, we just look at the perimeter. The fact is that in the upper half plane, when k has a positive imaginary part, this is exponentially damped. So that's the main reason why we get away with that. And then well, as an exercise, you can show that it actually is a ghost contour, and so this thing is just pi over 2. Any questions? I'll skip, well, maybe I should just mention Feynman's propagator. Feynman's propagator is, first of all, Feynman's propagator is a Green's function for a 4-dimensional Gaussian, which is written sometimes as box being triangle minus d by dt squared, and triangle, of course, is the ordinary Laplacian. Delta fourth of x is, of course, this integral, and we could have a plus or minus signs up here, it doesn't matter. On the other hand, there's some ambiguity in this function, because what we can have plus or minus I epsilon, or just 0 here, and it'll still be a Green's function for m squared minus box. And what Feynman did was he chose a particular thing, small number, to add to the denominator, minus I epsilon, because that gave all right, let me, I made a long gesture with my fingers. Anyway, this is an exercise in ghost contours to do to evaluate the Feynman propagator. And And then what eventually you find is that his choice, his choice of putting minus I epsilon there gives you the mean value in the vacuum of the time-ordered product of two scalar fields. And if you were talking about quantum optics, then you'd have the electromagnetic field here, you'd have A1 and A2 perhaps, and that would, or you'd actually want A1 and A1, and then you have something very much like the Feynman property. All right, the next topic is dispersion relations, and I don't know how far we'll get with this since it's already, we only have 5 minutes. But let me give you the basic idea. In many physical contexts, we're dealing with a cause and an effect. And there's a transfer function which represents the process by which the cause causes the effect. And if the system is causal, then this transfer function, only is non-zero when t is later than t prime, because a cause at t prime can only have an effect at later times. At least that's the way we think about cause and effect. And that means that this f is something that's zero for negative arguments. And so if you take the Fourier transform of the process of the transfer function, you just have an integral from 0 to infinity. And now you see, since t is positive in this integral from 0 to infinity, this thing is going to be exponentially damped as z goes up in the complex plane. Because you then would, if z is x plus iy, this would be e to the minus yt. So f of z is analytic in the upper half plane. And to get further with complex variable theory, we normally assume that the absolute value of f goes to 0 as you go out to infinity in the complex plane. That's so we can add a Gaussian contour. So if z0 is anywhere in the upper half plane, since we already have that f is analytic in the upper half plane, we can use Cauchy's integral formula to write f of z0 as an integral, and the contour is along the real axis, and then a Gauss contour around the North Pole. And on the other hand, since we've assumed that the absolute value of f goes to 0 on that Gauss contour, we have that the value of the Gauss contour is just 0. So we drop the Gauss contour. And f of z0 then is just an integral on the real axis. We then want to make contact with Cauchy's principal value, and so we bring z0 down to the real axis. And so we have f of x0 is 1 over 2 pi I, integral of f of x along the real axis, x minus x0 minus I epsilon. This gives us Cauchy's, we apply Cauchy's trick, and this becomes principal part plus I pi delta, and that gives us 1/2 f of x0 on the right-hand side of Cauchy's principal part. And now we combine this term with that term, and what we get is that we get then this dispersion relation, that f of x0 is 1 over pi I, the principal value of the integral of f of x dx over x minus x0. So this is something that's used a lot, well, not a lot, but it's used in electrodynamics, quantum optics, quantum mechanics, quantum field theory. It was remember I told you that there was a period back in the 60s and 70s when theoretical physicists fell in love with complex variable theory, and they milked dispersion relations for all they were worth. And there was a lot of nice stuff that was initially done by Gelman, Lowe, Mandelstam, I can't remember all of the people. Anyway, Adler, Stephen Adler. What one sometimes does is break, well, we're out of time, and I think we've gone, I'm going to explain dispersion relations again next Tuesday. So Thursday we're going to have this midterm. Think of the midterm as I said, I'm only having the midterm because I want you to, I'm just worried that you may not be studying it all. And so I'm hoping that you'll study hard the material for the first midterm. And to compensate for the first midterm, the final will only be on stuff that's not on the first midterm. Although, obviously, if you learn some mathematics in the first 4 or 5 chapters, you know, I expect you to remember it. It's just I'm not going to focus on that stuff on the final. The final will be mainly on complex variable theory, just differential equations, and the rest of the first 10 chapters. All right, I think we can end it.